All right, let's talk about something we've all been through. You build a machine learning model, it looks like a genius during training, but then it completely bombs in the real world. Well, today we're diving into the solution, a showdown between two super powerful techniques, L1 and L2 regularization. This is something every single one of us needs to have in our toolkit.
So you've got this classic machine learning mystery, right? You've trained a model that aces every test you throw at it on your training data. It looks perfect. But the second it sees new, real-world information, it just completely falls apart. What is going on here?
Well, this problem has a name, and it's a big one. Overfitting. The best way to think about it is this. Your model didn't just study for the test. It memorized the answer key. So yeah, it gets a perfect score on the practice exam, but it completely fails the final because it never actually learned the concepts.
And here's the thing. As we make our models more and more complex, adding more features or adding more layers to a neural network, we give them more power to do this. They get so powerful, they can start memorizing every little detail in the training data, including all the random noise and weird quirks, instead of learning the general patterns we actually care about.
So what does this memorization actually look like in the math? Well, it leads to these huge, really unstable coefficient values. The model starts clinging to noisy data points, putting way too much importance on specific features that aren't actually predictive. And that's what makes it so fragile and unreliable when it sees anything new.
So, how do we stop our models from, well, basically cheating? This is where a technique called regularization comes in. You can think of it like a coach for our model, teaching it some discipline and stopping it from getting too complex and way too overconfident.
Here's how it works. Regularization adds a penalty term right into the model's loss function. This penalty is tied to how big the model's coefficients are. So, during training, the model is forced to think twice about making any coefficient too large. It effectively pushes the model to keep things simple, general, and way more robust.
Now, this is where it gets really interesting, because it's all about how we apply that penalty. And that brings us to our two main contenders in the ring today. L1, which you might know as Lasso, and L2, also known as ridge regularization. At first glance, these formulas look almost identical, right? But that one tiny mathematical difference, using the absolute value of the weights versus squaring them, has absolutely massive consequences for how the model learns and what it ends up looking like.
Okay, this visual right here is where it all clicks. So the goal is to find the lowest possible error, which is the center of those ellipses, without our weights leaving the shaded penalty zone. For L1, that zone is a diamond. For L2, it's a circle. The best solution is the very first point where those error ellipses touch the shape.
Now, look really closely at that L1 diamond. Because it has these sharp corners that lie right on the axes, it is way more likely that the ellipses will hit one of those corners first. And what happens at that exact point? One of the feature weights, W1 or W2, becomes exactly 0. Poof, it's gone. The model has decided it's irrelevant. So that simple geometric difference leads to two totally different outcomes for our model's weights. And we call these effects sparsity versus shrinkage.
I love this analogy. Think of L1 as a really strict editor. It goes through your features and just cuts out anything it thinks is unimportant, driving their weights to 0. It's performing feature selection. L2, on the other hand, is more like a team manager. It doesn't fire anyone, it just reduces everyone's influence a little bit, keeping all the features in the game.
So the result of L1's strict editing is what we call a sparse model, one where a lot of the feature weights are literally 0. This is incredibly powerful because it does automatic feature selection for you. It tells you which features the model thinks are important and which are just noise, making your model so much simpler to understand. Now, L2's team manager approach is different. It shrinks all the weights and pushes them towards 0, but it very rarely makes them exactly 0. This approach is fantastic when you believe that all of your features have at least some predictive power. In fact, this is so common in deep learning it has its own name, weight decay. It's an absolutely essential, often default tool for training stable neural networks. Okay, so that covers the how, but the million-dollar question is when, right? When do you call in the strict editor and when do you need the team manager? Let's open up the playbook. You're going to want to reach for L1 when you have a ton of features. We're talking hundreds, maybe thousands, and you have a hunch that most of them are probably useless. L1 will clean house for you, giving you a much simpler and more interpretable model as a result. And you should definitely go with L2 when you think that most of your features are actually contributing something meaningful. It's especially good at handling correlated features, and it's just a fantastic all-around tool for preventing overfitting and improving model stability. Honestly, there's a reason it's the default regularizer in most deep learning frameworks.
All right, the bell has rung. Let's head over to the final scorecard and lock in the key takeaways from this showdown.
So here it is, the side-by-side comparison. L1, with its absolute value penalty, creates sparsity and acts as an amazing feature selection tool. L2, with its squared penalty, shrinks all the weights down, making it the go-to choice for building stable, robust models and preventing general overfitting.
At the end of the day, both L1 and L2 are all about managing that critical balancing act between a model that's too simple to be useful and one that's too complex to be reliable. And that leaves us with a final thought. Finding that perfect sweet spot between complexity and real-world performance, well, that's not just science, it's the true art of machine learning.